Hello everyone and welcome back. Today we're going to introduce a very important method that is used to solve linear programs by hand, which a lot of actual programs are implementing to solve linear programs for the general sense. And this method is known as the simplex method. There's so many things to talk about in terms of why the simplex method actually works, but in this video I'm actually just going to go through a very basic example of how the linear programming solution via the simplex method is actually generated, and then in the next video or discussion we'll talk about sort of, the ins and outs and the whys and the theoretical aspects associated to the simplex method. So to start, in order to use the simplex method on a linear program, the linear program must be in standard form. So if you don't know how to write a linear program in standard form, definitely learn how to do that first because the simplex method mandates that a linear program be in this particular format. In particular, it must be a minimization problem. There must be no constants associated to that linear functional that you're trying to minimize. The constraints must be equality constraints, and all of the variables x1 down to xn must be greater than or equal to 0 in their restricted formats. All right. So once you have a LP in standard form, then we can go ahead and write our problem in what we call a simplex method format. So let's just go ahead and give a nice little example on how some problems are going to be given to you. So let's assume our goal is to maximize the functional f of x is equal to 2x1 minus x2 plus 2x3 subject to the constraints that 2x1 plus x2 is less than or equal to 10, x1 plus 2x2 minus 2x3 is less than or equal to 20, x2 plus 2x3 is less than or equal to 5, with the restrictions that x1, x2, and x3 are all greater than or equal to 0. So the very first thing that we need to do in order to use the simplex method is to convert this into standard form. So we first need to convert this into a minimization problem. So the coefficients 2, minus 1, and 2 are going to be negated. And then we need to change these less than or equal to signs into equal to signs by introducing slack variables, say S1, S2, and S3. So once we do so, then our standard form is going to be equal to the minimization of the functional. F of x is equal to, so it's a different f, but I'm just going to call it f for now, minus 2x1 plus x2 minus 2x3 subject to the following constraints. 2x1 plus x2 plus s1 is equal to 10, so s1 is our first slack variable. Then we have x1 plus 2x2 minus 2x3 plus s2, that's going to be our second slack variable for equation 2. And then lastly, we have x2 plus 2x3 plus s3 is equal to 5. And then we have our x1, x2, and x3 is greater than or equal to 0. And that is going to be our linear program in standard form. So once you have it in standard form, the very next thing that you should do to start off the simplex method process is to create what we will refer to as the initial tableau. Tableau, tableau. So the initial tableau for the simplex method is going to be set up as follows. So we're going to have our x1, x2, x3, s1, s2, and s3. So those are all of our variables in our decision vector x. And then we're going to have our b column located there. So we have our x1, x2, x3, s1, 2, and 3 in B. And over here we're going to have our basic variables, right? And you should know the relevance of basic variables from our discussion for theoretical linear programming, because those help generate our extreme points or for our feasible region. So our basic variables, so of course we have our objective function z, and then we're going to default our basic variables to s1, s2, and s3. Now these are going to be our default. variables. Now we do not want S1, S2, and S3 to be in our optimal solution. Our goal is to move S1, S2, S3 into a solution ideally consistent of all of our X1, X2, X3. Sometimes that's not possible, but that's our ideal goal. So this is going to be our setup. So for our z functional in terms of x1, x2, and x3, we're going to have -2, 1, -2, and then we didn't have any slack variables, and that's going to be set equal to 0, let's assume. And then s1, then we're going to have 2, 1, 0, 1, 0, 0, and 10. 1, 2, -2, 0, 1, 0, and 20, and 0, 1, 2, 0, 0, 1, and 5. So this sort of big block rectangular matrix in the bottom, that's our normal coefficient matrix A. So A is located here, our little b is located there, and eventually what we want to do is we want to make that the value of our functional once we have that optimized. So currently, if we interpret this, what do we have? So currently, the solution is x1, x2, x3, s1, s2, s3 is equal to, so how do we interpret this solution? So x1 is going to be equal to 0, 0, and 0, and then 10, 20, and 5. Now, where am I getting these numbers from? So our basic variables are S1, S2, S3. So if S1, 2, and 3 are our basic variables, that means our null variables are X1, 2, and 3, which we default to be equal to 0. And that's going to be our basic XB solution to our optimization problem. Now, it's not possibly, well, it's possible that this is our optimal solution, but I'm pretty sure we can get a profit or an optimal value bigger than 0 if we're trying to maximize, or smaller than 0 if we're trying to minimize, right? But at the present time, 0, 0, 0, 10, 25 is a solution to this linear programming problem, but it's not the optimal solution, right? So definitely check that out, and if you don't know, basic variables and basic solutions and basic matrices and things like that. But of course, this gives us a functional value of 0. Right? So the next thing, so step 1 of the simplex method is as follows. So we need to identify the entering variable. So we need to identify the entering variable by choosing the variable associated to the most negative entry of our optimal objective function z. So let's go up here and look at our row of z. So notice that we have -2 and -2 tied for the most negative. We're going to default to use x1 as our entering variable. So I'm just going to sort of ignore this other -2 here, but you'll get the same exact solution if you go ahead and do x3, and I invite you to try that in case you're interested. So what I'm going to do is I'm going to highlight that first column there. So x1 is my entering variable. So entering variable in our first iteration of the simplex method. Then I need to target, so let's actually state that here. So the entering variable is x1, or you could do x3, but I'm not going to go about it in that way. I'm just going to choose x1 because 1 comes before 3. So the next thing we need to do once we have chosen our entering variable is to select the departing variable for the first iteration of the simplex method. Keep in mind, since we only have 3 rows associated to our coefficient matrix A, we can only have 3 basic variables in order to construct a 3 by 3 matrix, a square matrix, to sort of set, to invert and multiply by our coefficient values B. Therefore, if we have our entering variable, in this case we're entering x1 into the picture, that means one of our slack variables s1, 2, and 3 need to get out of the picture. Because if x1 enters, that gives us 4, that means 1 needs to be removed, i.e. a departing variable, so we need to figure out which one to remove. So if xj is the entering variable, in our case that's going to be x1, we need to calculate our bkj's, our constants on the right hand side, divided by our coefficients aj in that particular row. Okay, and then choose the least positive one of them all. So let's actually go ahead and write out our initial tableau again to sort of see what's going on here. So again, we have x1, x2, s3, x3, s1, s2, s3, and b. And then we have z. Then we have s1, s2, s3 as our default basic variables. And then we have -2, 1, -2, 0, 0, 0, and 0. And what did we have? We had 2, 1, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1 there, 10, 20, and 5. And then we had what? 1, 2, -2, 0, 1, and 2. And we chose x1 to be our entering variable. So what are we going to do? So we're going to take all of our bk's, which are going to be 10, 20, and 5, and divide by these coefficients in that particular column vector. So we're going to do 10 divided by 2, 20 divided by 1, and 5 divided by 0. So 10 divided by 2 is going to be equal to 5, 20 divided by 1 is going to be equal to 20, and 5 divided by 0, let's just define that to be equal to positive infinity just for the sake of convention. So out of all of these numbers, 5, 20, and positive infinity, which one is the least positive one? That's going to be equal to 10 divided by 2, and 2 was associated to the first row. Therefore, my departing variable will be S1. So S1 will be my departing variable, and x1 is going to be my entering variable. And this coefficient 2, that's going to be my pivot. So that's going to be my pivot for Gauss-Jordan elimination. So remember with Gauss-Jordan elimination, what we need to do is we need to make that 2 equal to 1, and we need to make that -2, that 1, and that 0 all equal to 0. So we're going to be focusing on that particular column where the entering variable is going to go. And then we're going to be changing S1 to X1. All right, so let's just state that here. So step 3 of the first iteration is make the chosen pivot equal to 1 and all other values in that column equal to 0 via Gauss-Jordan elimination, which we should know how to do already. And also keep in mind, S1 departs and X1 enters and replaces S1. So let's go ahead and go through that process. So now we're going to generate the next tableau. So we're getting rid of our initial tableau and we're going to the end of the first iteration. So how are we going to do this? So what we can do is we can add row, I'm going to call this row 0, row 1, row 2, and row 3 for Gauss-Jordan terminology. To get rid of that -2, we can just do row 0 plus row 1 to eliminate row 0. We can do 2 times row 2, subtract from row 1 to get a new row 2, and then we can, we don't have to do anything to row 3 because that's already equal to 0. Right? So let's just state out that process. So for example, row 0 plus row 1 can get us a new row 0, that's for our z. And then we can do row 1 minus 2 row 2 to get a new row 2. Row 3 is going to remain fixed. And then we'll divide by the coefficient to make it 1. For example, we can do row 1 divided by 2 to get a new row 1. So once you perform these, we get a new tableau. So let's just write that out. So we're going to have z. Then we're going to have x1, x2, x3, s1, s2, s3, and b. And then our new basic variables are going to be x1 because x1 replaced s1, but we still have s2 and s3 here. All right, so we're going to have 0, 2, -2, 1, 0, 0, and 10, 0, 1 half, 0, 1 half, 0, 0, and 5. 0, minus 3, 4, 1, minus 2, 0, and minus 30, and then 0, 1, 2, 0, 0, 1, and 5. So that is our next tableau. So we repeat those same exact steps like we did for iteration 1, but now we're on iteration 2. So the first thing we need to do is look in our row of z and look for the most negative value that's going to be located here in the column of x3. So x3 is going to be our entering variable. Now we need to figure out who our departing variable is going to be. So what we need to do is we need to take our coefficients, 5 minus 30 and 5, and divide by 0, 4, and 2, and see what those coefficients are, and choose the least positive one. So again, we're going to have 5 divided by 0, negative 30 divided by 4, and then 5 divided by 2. So that's going to be equal to positive infinity, that's going to be equal to minus 7.5, and that's going to be equal to 2.5. So 2.5 is the least positive of them all. So that's going to be equal to row 3. That means my departing variable is going to be equal to S3, my entering variable is going to be X3, and my pivot is going to be that 2 that I've just shaded in blue. So our goal is to make that equal to 1 and make that 4, that 0, and that minus 2 all equal to 0 via Gauss-Jordan elimination. So let's just write out the steps that we would do in order to carry that out. So again, we have our z row plus row 3 to get a new row 0, and then we're going to have row 2 minus 2 row 3 to get a new row 2, and then we're going to do row 3 divided by 2 to give us a new row 3. And we don't have to do anything to that row 1 because it already has 0 in that particular location. And keep in mind, S3 is departing and X3 is entering. By chance, they have the same index. They're not always going to match. Sometimes S3 will depart and X2 will enter in its position. So let's write out our second tableau in our sequence. So we're going to have X1, X2, X3, S1, S2, S3, and B. And then we're going to have z. And then our basic variables are going to be x1, s2, and x3. And what are going to be our values here? So we're going to have 0, 3, 0, 1, 0, 1, 15, 1, 1 half, 0, 1 half, 0, 0, and 5, 0, 5, 0, minus 1, 2, 2, and 40. Those used to be negative, but I've actually just changed the sign because you'll see in just a moment why I want that to be. And then 0, 1 half, 1, 0, 0, 1 half, and 5 halves. So remember that this is a pivot, this is a pivot, and notice if I look in the column of S2, that should be a pivot as well, because notice I have 0, 0, and 0 there. Because if I want to go to, for example, a third iteration of the simplex method, I would look at the most negative coefficient of z, but it doesn't exist, right? So notice that all of the coefficients that are here are all positive. That's a good thing, right? That should make you happy. That means you're pretty much done with the simplex iterations. So what we need to do is we need to make that equal to a pivot, right? Because those are our basic variables. So we need to just divide row 2 by 2 in order to get a new row 2. So what I'm actually just going to do is I'm going to just delete that, just divide those things by 2. So that's going to give us 0, 5 halves, 0, minus 1 half, 1, 1, and 20. Okay, so there are our 3 pivots. And once all of these things are positive, then we're done. So what is my solution? So my optimal solution, according to the simplex method, is going to be what? So x1, s2, and x3 are our basic variables. So all of the others are going to be our null variables. Therefore, they're going to be defaulted to 0. So that means we're going to have x1, x2, x3, s1, s2, s3. Notice that the optimal solution doesn't have x2 in it, and that's okay because s2 is picking up its slack. So our optimal solution is going to be equal to 5, and then we're going to have 0, and then we're going to have 5 halves for S3, and then S1 doesn't exist, S2 is 20, S3 is not one of our basic variables, that means going to be equal to 0. And then that generates a minimum of minus 15 or a maximum of 15. Either one of them would be accurate interpretations of this tableau. So that is pretty much an introduction of how you would carry out the simplex method. In our next discussion, we're going to do a more complicated version of the simplex method and dive into a couple of the theoretical aspects of why the simplex method actually works. But until then, I hope you take care. Thank you.